Hello students, in the previous class we have discussed how to do linear measurements on ground. Today we are going to discuss about the measurement of the directions of survey lines. We always know in all practical situations our survey lines are never straight. And if you are calling the line is straight with reference to your eyesight, you are telling that the line is straight. But if I take any other reference, then that line may not be a straight line. So what is the point which I would like to make is, if you want to state a survey line as a straight line, there is always a reference to it. So straightness is what we wouldn't follow in surveying. We always keep some kind of a reference when we are talking about the direction point of view. So the reference is our angle. Imagine a protractor. A protractor is a similar circular shape. You have 0 to 180 degrees and it's graduated in clockwise direction. Now, I can draw any angle with a reference. So the point is, in order to draw any angle on a piece of paper using protractor, you need to have a reference. So on ground, so what is our reference? Now, we don't have a paper pen there. So we take a geographical north as a reference, which is a sort of common, I would say. But it is not so common, we will discuss it later. Let me show you a small map for you. I've drawn it in PowerPoint, you can see. Now, concentrate on the image which I have shown there. I've drawn a road, or with reference to road, all the buildings were constructed. This is the plan which I am talking about. Think about any city, and this image was taken at an altitude. Altitude is, it's some height, a camera is set up, then you have taken a picture and you have drawn as a map. So if this is the situation, you can see that road is not straight there. Immediately say, you say that road is inclined. So you always have some kind of reference point if you want to talk about the inclination of the road. Perhaps if you concentrate a little bit more into the shapes of the buildings which I have shown there. There is one building which you think is straight. That is the plus symbol which I have drawn there. Correct? Now you are saying that the plus symbol is in straight line because the lines are parallel to my PPT. Rest all are parallel to the road, you are saying that the building is inclined. But imagine you are traveling on the same road. You have a vehicle, you are traveling on the same road, then you think that all the buildings are in parallel or say in a straight line. So in a plotting of any map, it is not just important to have the linear measurements, which means lengths of the lines. It is also important to know the angles of those lines. This is very important when your land is undulating, you have a very bad terrain conditions there. You have so many details in the land where chain survey or your tape survey couldn't able to get those details, right? So in these conditions, compass is an instrument or angular measurements are very much useful in drawing the map. When the land to be surveyed is not a plain field and you have undulating terrain, then you'll go for angular measurements. And even if the land to be surveyed has so many details, like you have trees there, you have a small drain there are so many details which you have to furnish on a piece of map, then even you need some angular measurements in order to point it out on map. It is very cumbersome if you carry out chain along with you and imagine that you can draw all these points with those instruments alone. So in chain surveying we use a principle of triangle where we divide entire field into number of triangles in order to get our details or draw the map without errors. Whereas when you do compass surveying, we'll do traversing, which is it's a principle of compass surveying by itself. What is traversing? Traversing is interconnected lines which has a certain direction to it, or it's a framework consisting of connected lines. In the figure you can see there is a point A, there are point B, point C and so on, and these lines are connected all together along with the lines and also the direction with reference to the north. Now imagine you are standing at A. Imagine you are standing at A and you are looking at point B. It means that B point is inclined with some angle with reference to north. And where do we get north from? We use an instrument called compass along with us. Now we'll study in detail about compass. When you are doing this traversing, you will also calculate the lengths of these connected lines using chain or a tape. Now using an instrument, it can be a compass or it can be any instrument, you can easily identify the angles and plot it on a piece of paper. There are 4 different major types of instruments where you can calculate angular measurements, which are box sextants, compass, theodolite and total station. Box sextant is a very old instrument. It is used for very low angular measurements. Whereas compass surveying is pretty much used in majority of all the surveys, where it uses the magnetic needle which always shows the geographical north. We'll talk about geographical north in next class. Now we'll also have a theodolite where you need not have a geographical north as a reference but a fixed stationary point as a reference, and you can easily calculate the angle subtended by the other line. Then you have a distance instrument which call it as a total station, where within minutes or within seconds you can easily calculate the angular measurements. Compass is an instrument which is used for navigation and orientation of the direction of the line. It is predominantly used by sailors when they are on sea, on ship. So whatever the figure you are seeing there, it is called as a rose. And you can see north, east, west and south. A compass is a magnetized needle. When you suspend freely, it will show geographical north. Often, compass is designated with markings north, northeast, southeast, southwest, along with the angles measured in clockwise direction, 0 at north, 90 degrees at east, south 180 degrees, west 270 degrees, as shown in the figure. Using this magnetic needle, which is freely suspended, we can easily calculate the angle made by the line with reference to the north. But first of all, you have to know why actually a freely suspended magnetic needle shows north. I would like to take you the explanation of an expert
in the following video.
How does the Earth generate its magnetic field?
Okay, so the Earth self-generates a planetary scale magnetic field in its core. So let me first mention that here's Earth. We live right there, and that's us not to scale. Right now our head is far out in space, right? We would quickly perish. But here's our planet, and if you cut a cross-section through it, the inner half is actually predominantly liquid metal. However, the pressure gets so high in the middle that the innermost third has actually solidified. So this part's solid, this part's liquid. It's all predominantly iron with some nickel and some other stuff. So let's say it's mainly iron, nickel, and other stuff. I'll for today just say sulfur. Could be a couple things, but we'll choose sulfur. Okay, so here's our planet. We've got, for the most part, solid silicate in what's called the mantle. And this core is about the size of Mars. It's big. It's the size of other planets. And it's predominantly, volumetrically, it's predominantly liquid. And this planet, our planet, all planets, are radiating heat out to space. And that causes the mantle actually to be overturning.
But if it's solid, how is it overturning?
It's overturning on about a 500 million year time scale. It's solid state convection. This is the beauty of plate tectonics. It's a whole nother story. But the mantle is overturning roughly every 500 million years. Really slow. And yet we can map it all out. It makes a lot of sense. Okay, so very slow overturn of the mantle. That, though, is allowing heat also to escape from the core. So the core is cooling down as well as the mantle. And as the core cools down, one of the most interesting things is that as the temperature decreases, the inner core grows outwards in time. So this inner core is freezing from the center outwards. It's like an inverse candle. It's actually freezing outwards. It's crazy. And what else is interesting is the inner core is almost purely pure iron. So when it freezes, it's releasing a lot of this light sulfur, or whatever that extra element is, at the inner core boundary. That's what it's called. And so you're releasing light material here, and it's floating up, and you've got convection in the outer core due to the, predominantly right now, due to the freezing of the inner core. There's also cold stuff falling down from here, but we're gonna say, for various reasons, as the inner core forms, you drive a lot of turbulent convection in the core. Okay, so crazy weird planet, onion structure, inner core growing outwards. Now, where's the magnetic field come in? Well, okay, so here's our core again. The large scale magnetic field looks a lot like a dipole magnet. It's tipped a little bit off, but it's not far from the rotation axis of the Earth, about 11 degrees over. Okay, so roughly an axial dipole. It looks from the outside somewhat like a giant bar magnet, except when you look in detail, everything's moving around. We see all these little flux patches, and they're all trucking around fairly fast. So it's not some big static bar magnet, but it does have a similar structure. Most of the energy is in what's called the dipole, the bar magnet part of the field. Okay, so now we've got some magnetic field in this liquid metal. What's amazing is the liquid metal is convecting fast enough, so let's just worry about this piece right here. So there's some fluid motion goes in the region where this magnetic field is. It will actually stretch it and drag it off to the side. And when it does, it actually generates new magnetic field. So the magnetic field gets trapped in the fluid in Earth's core. And the motions of the fluid then drag the magnetic field and generate more magnetic field. So if the fluid motions generate magnetic field through this stretching effect faster than the magnetic fields diffuse away due to the resistance of the metal itself, then you can get a magnetic field. And so if you imagine this flow is going really fast, oh man, it might wrap the field into a couple of big loops. Okay. So maybe there are huge loops of magnetic field inside the Earth's core, and actually we expect there to be. And now if there are other motions that twist these the other way, then you'll get other loops, and other loops, and other loops, and they may all add up to creating a large-scale field. So it's a big turbulent process where we're constantly dragging the field around faster than it goes away, and if we do so in the right way, we'll generate this axial field. Here's some solid inner core. And now let's imagine we just have a magnetic field line wrapping around in a big loop.
Where's that magnetic field coming from?
Along some line of latitude. Let's start by just imposing some torus of magnetic field.
Okay. That's fine.
I'm being very friendly.
We've
to
got
myself.
initial conditions.
Yep. And now let's take a flow that moves upwards and that also has a little rotation to it. So it's a little helical motion. What's it going to do? It's going to take this magnetic field, it's going to get stuck in the flow, and it's going to make a little loop out of it. Well, anytime you have a loop of magnetic field, that means I can draw a little current vector through it. Right?
This is so unusual because normally I think of the current and then I draw the magnetic field of the
I know.
current.
I think the other way. So now, let's let there be a bunch of these little helical plumes everywhere. What will we do? We'll generate a bunch of these little loops all the way around, and they will spawn little currents, and if we get it right, we'll form a large-scale ring then of current. If we add all these up, that large-scale ring of current is then going to produce a large-scale magnetic field coming through it. So we can have little motions, but if they're organized correctly into a bunch of helices, for example, then we might expect to generate large-scale currents. That will be fairly well organized and will generate large-scale magnetic fields. So let's figure out why might we have helical flows in our system. And the answer is that it's really, you can think of it almost as ice skater theorem for angular momentum. Whenever we get a plume, let's say leaving, for instance, the inner core, the material actually, when it enters that plume, it comes in from both sides. Well, when it comes in from both sides and erupts upwards, that's really the ice skater pulling its arms in. It's in a rotating system, and now the plume has kind of stretched vertically, the fluid. Well, when it does, it causes it to spin. So when the fluid goes upwards, it tends to acquire a net spin in one direction or the other. Well, that's a helical pattern. So you naturally have helices when you have rapidly rotating convection. And so what do those helices do to some background field? Yeah, they typically generate a lot of fairly well-organized little current patches. And those can all add up, we hope, to large-scale fields. And actually, I have one side note. The first person who proposed a fluid dynamo was Elsasser. Back in I think he first proposed it in the 1950s. He took the idea to Einstein and said, what do you think? Nothing else works. How about a fluid magnetohydrodynamic dynamo in the core? And Einstein said, oh, it's messy. You're wrong. And Elsasser was very sad. But about 60 or so years later, no, he was right. He nailed it. It's just complex.